So in the last video, we took a look at why we might need a new method to help us find volumes of solids that were obtained by revolving a region around an axis. So we're going to take a look in this video at the cylindrical shell method to kind of figure out what it is. Now I've included a little link here in our notes to help kind of illustrate what this new method is so we can see that it is going to be a dx method for allowing us, at least in this question, to find the volume of this solid. So I'm going to go ahead and follow this link here really quickly. Let's see what we come up with here. So you can see I have a region that's very similar to the region that we had on the previous page. And what you'll see is that I'm first going to start by dividing up that region into smaller individual sections, little rectangles if you will. And I'm going to imagine what happens as I rotate each rectangle around that y-axis. Remember, that's what we were trying to do with the problem in the last video. And so you'll see what I create here is a shape of a cylinder. Although it's not solid all the way through, it's kind of hollow in the middle. And if I was to do this for every single one of my starting little rectangles that I created here, I could start to see that I kind of create this nested sort of shells or cylindrical shells. And if I kind of capped them all off, rotating them the full 360 degrees, they all start to layer around each other. And this gives me at least a rough approximation of the actual solid, which would look something like this. So that original kind of again, nested shells or nested cylinders was close to this shape. It provided an approximation. And so what we would want to do is to be able to find the volume of those individual cylindrical shells, the ones that look like this picture down below. If I could find the volume of that, that would be great. And then if I knew the volume, I could add up all those individual shells, and if I could add them all up, I could then easily go ahead and take a limit as the number of shells that I use goes off to infinity. That would make each of these shells much, much skinnier because my starting rectangles would be much, much smaller. And you can almost kind of simulate this on your own if you have like a stack of paper anywhere. You can imagine that if you curl this paper, you kind of curl it up into a rod of some sort. What you're seeing there is that each individual piece of paper acts as a thin layer that's contributing to the overall figure. And that's what each of our shells is doing. It's a thin layer that's kind of slowly building up and creating this solid. So to kind of see how this is going to work, let's take a look down here and write out some of the detail. So again, I'm going to imagine that I'm going to take a rectangle that's over here, and I'm going to start to revolve that rectangle around my y-axis. That's where I'm going to spin it. And let's suppose that that rectangle exists on some range of x values. We'll say that xi is the right side, and xi minus 1 is the left side. This is just a way to number our x's on our x-axis. Now we'll say that this point here, where I'm going to go up and determine the height of my rectangle, a point that we would normally call xi star, let's just call this for the moment xi with a bar on top. That bar usually indicates that it's an average of the two endpoints, and that's exactly what we're going to treat it as, that this is like the midpoint here. It's an average. So we'll start by kind of writing out the following detail. Our goal right now is to find, so I'll say we want to find the volume of a shell. We want to find the volume of this kind of orangish shape here. And so to do this, we will find the volume of the, oops, that is a very awkward the. We'll find the volume of the outer cylinder and subtract the volume of the inner cylinder. This is going to be actually a very similar process to kind of how our washer method worked in the last section. Notice here, if I can find the cylinder that goes all the way out to this edge. So just imagine this outer ring, this kind of big circle up top. There's a big cylinder with a big volume. And since this middle part is hollowed out, something you could imagine like sticking your hand through, then I can go ahead and find this smaller radius, which would exist in here, find that smaller cylinder's volume, and kind of subtract it from the bigger one, punching it out of the middle, if you will. So we're going to go ahead and try to figure out again how exactly we could do that. So here's what we'll start by describing. We'll start by stating that first our sample point is our xi bar. Remember, we said that was the average of the two endpoints. That is, it's the midpoint. And so of course that means we would get this by doing x sub I, adding x sub I minus 1 and dividing by 2, right? That's how you get an average. You add the two things up, you divide by 2. That would get us the midpoint. So now notice it would be really, really easy to find the volume of our individual shell. So the volume of the shell is given by, and let's see how we could do this. I'll start here by just saying this is my volume of shell number I. Okay, and I know that the volume formula for just a regular cylinder is pi r squared. It's like the area of the top circle, and then multiplied by the height. So I'm going to have the same basic shape here. I'm going to have my pi times my r squared times my height. Now I'll notice here that if I wanted to find my r, my r value here, I'm going to have to see, how far is it to go from, again, this point over here all the way to the edge of that outer cylinder. Well, actually, if I bring this kind of line, this black line here, down to the x-axis, I can see that I actually stretch all the way out to xi. And so the length of this segment here, same as the length up there, should be xi. So my radius here is xi. And so I'm going to do pi r squared. That gives me area of the top circle. And I multiply that by how tall that cylinder is going to be. But notice again that we have, if xi bar is my midpoint, and that's determining the height of my rectangle, then f of xi bar is going to tell me my height. So this is the volume for that outer cylinder, and what we have to do is subtract the area of or the volume of that inner cylinder, which should follow pretty much the exact same formula. Notice that here I'm still going to have to do a pi r squared times the height, but my r now is going to stop at this edge of where that inner circle lands. And again, if you were to bring this line down to the x-axis, you can see that I would stop right here at xi minus 1. So this is xi minus 1 squared. Oops, and let me rewrite that inside there a little bit cleaner. Xi, and that minus 1 is down in the subscript. The height, notice, is exactly the same. It's fxi bar. So once I have this, and this represents the volume, I'm going to go ahead and attempt to clean it up a little bit to make it a bit easier to work with. So what I'm going to see here is that if I have these common values that actually exist here. I have a pi and an fxi bar that exist this, as common factors of each of these individual terms. And if I factor them out, I can think about what I'd be left with. I'd have an xi squared minus this xi minus 1 quantity squared. Now, I can go ahead and simplify this a bit more by recognizing that what I have here in this set of brackets is actually a difference of squares. And so I could rewrite this again as f of xi bar times my pi. And then over here, I could rewrite this as xi minus 1 times xi plus xi minus 1. Notice again, I'm just doing a difference of squares there. But once I have this, there's a couple other things that I could do. You'll notice that, and I'll put this here in a different color, but my xi minus my xi minus 1, if I think about what that looks like pictorially, that's this point over here on the x-axis minus this point on the x-axis. But if I think about what that measures, isn't that just the length of the interval? And what do we always call the length of our interval? Well, that's our value delta x. That's the width of a given rectangle. So this is fantastic. Notice that then I can go ahead and simplify this just a bit further into a pi fxi bar. I can have a delta x, and then I still have this xi plus xi minus 1. Now this last piece over here, I'm going to go ahead and actually be able to replace as well, because what you'll notice is that this down here actually looks extremely similar to this formula we had for xi bar, which remember was the average formula for these two endpoints. The only difference is that this has a divide by 2, and we don't have that. But I'm going to go ahead and create it. I'm going to go ahead and just say that I'm going to take this quantity and divide by 2, but then of course to counterbalance that I'll just multiply by 2. So of course my two red 2's there would cancel out, but if I leave them positioned in this way, I can then state that this is going to turn into a 2 pi f of xi bar times, notice here I can also have now my delta x, and this part I can turn into an xi bar. Okay, so I totally understand this probably feels like a whole lot of really weird and unnecessary work, but it's gotten us to something that's extremely valuable. Notice that I can say that the volume VI is then going to be equal to 2 pi. I'm going to rewrite the terms here just a little bit. And I'm going to have an f of xi with the bar, and then I'm going to put my delta x at the back. If I wanted then to go ahead and add up all of these, notice I could then say that the volume of the entire solid is going to be roughly equal to taking all of these different VI's and adding them up. So start at like cylinder number 1 and go to cylinder number n. And so we would expect then that if I was to go ahead and put a limit on this, so that is I don't let myself use just maybe 10 of these shells or 50, but I let the number of shells go off to forever, then I can state here that if I'm going to replace VI here with what it's equal to, that this would actually then represent the entire volume that I'm going to end up with. The entire volume. And again, here's the best part. Just like what we talked about at the start of section 2.1, this should ring a bell. This should look like a definite integral. Because notice, I have my limit, I have my sum. Over here, you'll see in green, it looks like I have a really messy looking function with a special xi bar plugged in, and I am multiplied by a delta x at the back. So this actually looks like an integral that goes from a to b. Notice that's kind of where my original rectangles would have started and stopped. And then I have a 2 pi in x in f of x dx. And this here would be an integral that represents the volume of this solid, but not calculated with washers, not calculated with discs, but calculated with these new cylindrical shells. If you take a look here at the next page, you'll see that I've kind of summarized this in the corresponding box down below. And I state here, if I'm working with a vertical axis, like I'm spinning around the y-axis, and so I can see these shells are going to wrap around each other, notice that they'll tend to kind of increase the layers and the width kind of in this horizontal direction. Every time I lap another layer on, I'm increasing the thickness left to right of the overall solid. That makes it a dx problem. And you'll notice here that I can see that I have a slight modification of the formula or the integral that I had in the previous page. Notice I still have the 2 pi, I still have the bounds of a to b, but I've kind of replaced this value of x with an r, and this value of f of x with an h. Now I'm going to show you in just a moment how exactly I can understand these values in that way. But for the moment, let's quickly see how this would work if I had a horizontal axis of rotation. If I had a horizontal axis of rotation, notice that would be like just imagining taking this page and just rotating it like 90 degrees. So maybe the y-axis pointed outward like this, and the x-axis you could imagine maybe pointing downward. If I had rotated it so the solid was at least generated looking that way, then it would be the case that every time I add another layer, I would be adding thickness in a vertical direction, right? Because I could imagine like a small cylinder existing here, and then I wrap another cylinder around it like this. Right? So as I continue to increase thickness, I'm expanding it in a vertical direction. So this would be a dy problem, and notice that the setup again is exactly the same. I still have this r and this h, but the only difference here is that instead of these representing something with x's, they'd have to represent something with y's. Now before we go ahead and end this video, I want to show you this connection between these values of x and f of x, these values of r and h. And to do this, I'm going to go ahead and draw one final picture down here on the page. What we've seen is that we've found up above how we could give a estimation of the volume of one of these individual cylindrical shells that looks like this. To see, though, how I get to this r and this h value, I'd like you to imagine really quickly that I could take this shell and maybe just cut it along one of these edges. And if this was some sort of like a loose material, maybe I could lay it out and I could flatten this thing. And notice that if I was to kind of flatten this thing out, the shape that I would get would look something like this. You can almost see this exact sort of behavior existing if you were to take a piece of paper and actually imagine sketching it wrapping up a piece of paper. A piece of paper is going to look something like our picture at the right side here. And if I imagine taking one of my edges over here and wrapping it around until I connect it back to that edge, I'll start to put things into the shape of a cylindrical shell. Now when I do this, I'll see that it's actually really obvious why I have a 2 pi x f of x dx and why I've called that an r and an h. Now take a look over here. We wanted the volume of this cylindrical shell, and I'm proposing that if I make this cut and flatten this out, these things have ultimately the exact same shape. Or, well, the exact same volume, because they came from the same shape. So notice that if I was to take a look over here, this cylindrical shell over here had a height, right? Now notice that it's going to be the same height that corresponds to over here. This cylindrical shell had a thickness that would have actually been given by the thickness of one of my starting rectangles. Let's just call that thickness delta x. And notice that that thickness is going to be repeated over here as a delta x. Notice that's kind of playing the role of our dx. Notice that my height is playing the role of f of x because my function helped me determine that. The only other dimension I would need to find the volume over here would be this length that I have on the side. Right? How long is this thing? If I knew that, I could easily find the volume over here. Well, notice that this length, when wrapped back up, corresponds to this distance around the outside of this circle. And how do you find the distance around the outside of a circle? Well, that would be the circumference, which notice would be something like a 2 pi r. And so if I have a 2 pi r, notice I can find the volume of this sort of a figure here. I would do delta x times an h times a 2 pi r. That would get me my volume. And notice that's exactly what we have here. So oftentimes this is how I choose to remember this idea. I choose to just remember that again, I can just see a little cylinder and I'm going to make a cut on it to unwrap it. You can use like a piece of paper every time to go ahead and imagine how this works. And then you can say, yep, there's a common h, there's a common 2 pi r, and then there's going to be a little bit of thickness to this edge wall, which we call delta x. And so to find that volume, I multiply all of those together. So we'll see how this works in a very specific example in the next several videos as we explore how this idea relates to the previous ideas in the previous section and do a little bit of comparing and contrasting in the difficulty of using each of these techniques.